This is waves 3. I'm just going to walk through sort of the reasoning and then some of the questions as we go through this. So let's begin. At the open end of a pipe, there always has to be an antinode, because at the open end of the pipe, that's where we're going to have our most displacement. However, at the closed end of the pipe, we need a node because that is the place of least displacement. So as we're thinking of something that is closed on one end and open on the other end, the best thing to think about would be a tuning fork. With the tuning fork, you have two half open, half closed resonators attached to each other. They're the arms of the tuning fork. And so the fundamental would be this thing moving to where that part of the tuning fork doesn't move at all, and that is maximum amplitude. And then these are the shapes sort of in this red box that would form there. All right, so those shapes are the ones that we will see on a resonator that is going to have an antinode at one end and a node at the other. So number 3 is just talking about what we see. And so we're showing the same 5 wave shapes that we've shown for closed-ended resonance so far, but this dashed line is where the open side of my tube is, and this distance is L. So for my first wave shape, that's only a quarter of a wave. So we're dealing with quarters of waves this time, not full waves. Draw the same length of pipe around each of the other harmonics. The open end of the pipe stops at the dotted line. So the other harmonics would have a pipe that looks like this. So as we're increasing the frequency and the wave gets shorter, the wavelength gets smaller, I can fit more and more and more wavelengths into a given pipe. And that's a good thing. That's how we get these standing waves. Now, which harmonics can be produced? In order to find if something can be produced, we need to find this which have an antinode at an open end. Otherwise, we don't meet the first 2 conditions that we have, which means if this is the first harmonic, this is the second, this is the third, fourth, and fifth, I cannot form even harmonics. So just the odds. Because even harmonics give me a node at the open end, and that won't resonate in this shape. So that's out. N can only equal odd numbers, so 1, 3, 5, 7, and so on. Since 2 full antinodes like that is 1 wave, the first harmonic in this diagram is a quarter of a wave. This is the amount of wave that we have in here. That's a quarter of an entire wave shape. So if we resolve that, all right, so if we solve that for lambda, lambda equals 4L. Okay, so we erase this and kind of do it in a different color. Well, so this is L is equal to 1/4 of a wavelength. So the wavelength here is equal to 4L. We don't get a harmonic from this. So let's see what goes on here. Now, since we don't get a harmonic for that, I don't care about it at all. But that's a full half of a wavelength. Here I have 1/2 and 1/4 wavelength. That gives me L is equal to 3/4 lambda. If I solve that for if I solve that for lambda, lambda is equal to 4/3 L. This doesn't give me anything. That is 1/2, 2/2, 2.5 halves. All right, so that's 5 quarters. 5 quarters of a wavelength. So one wavelength here is equal to 4/5 L. So the ones that don't exist are halves. We're not really about that. So write the equation for the wavelength of a harmonic in a closed pipe. So if we look at what's going on, that's 4L over 1, 4L over 3, 4L over 5, where this is n equals 1, n equals 3, and n equals 5. So lambda for a closed pipe is going to be 4L over n. Calculate the wavelength of the third harmonic in a 60 centimeter long closed pipe. So we're just going to use that. Lambda is equal to 4 times 60 centimeters divided by 3. That's going to be 80 centimeters. Now this is an open pipe, so we're kind of shifting gears. We're going to something that's open on both ends. But if we're open on both ends have to have antinodes. In order for a pipe to make a sound, it's got to have a standing wave, meaning it has to have at least one node and one antinode, possibly more. So for each successive harmonic, the number of antinodes goes up by 1. And then for each successive harmonic, the number of nodes also has to go up by 1. We're going to add one more every time. So we're going to draw the next harmonics. I've got one node. I'm going to move on to having 2 nodes. That's the next time I can fit a shape in that has an antinode on both ends. Now I'm going to have 3. Nodes, and that gives me so 1, 2 antinodes, 1, 2, 3 antinodes, 1, 2, 3, 4 antinodes, and then the last one, adding an additional node. Here the number of nodes is telling me my harmonic. That's really the big difference between a string wave. So on a string that's going to be clamped at both ends, you count the number of antinodes to figure out which harmonic it is. For an open pipe, you count the number of nodes to figure out which harmonic it is. Which harmonic can be present in an open pipe? All ends are possible. This is n equals 1, n equals 2, n equals 3, n equals 4. All of the ends are possible there. Because each one of those shapes is going to give me, figure out the sequence and give the equation for lambda in an open pipe. Okay, so we know that's n equals 1, 2, 3, and 4. So what we're going to do is say, all right, looking at this wave shape, that is half of a wave. So in L we have lambda over 2. The next one is a full wave, so in L we have 2 lambda over 2. The next one is a full wave, and then another half, so that's 3 halves of a wave. And then down here we have 4 halves, or 2 full waves. And if we solve each of those for lambda, we'll just kind of move over here. Lambda is equal to 2L. Lambda is equal to 2L over 2. Lambda is equal to 2L over 3. And lambda is equal to 2L over 4. That's the pattern here. So if we want to take that and apply it a little more broadly, give an equation. If we look at that, lambda is equal to 2L over n. And again, that's for all n's. So if we want to use that, lambda is equal to 2 times 80 divided by 3. So when we do lambda is equal to 2 times 80 divided by 3, we end up with 53.3 centimeters. Now we're just going to do a full pipe. An open pipe 3 meters long produces a 56 hertz sound at its natural or fundamental frequency. Since it is an open pipe, the fundamental wavelength is equal to 2L. Okay, so it's an open pipe. We're dealing with this shape. This is the fundamental, the first thing we can fit on here. And that's 1/2 of a wave is equal to the length. So twice that length is equal to L. So the wavelength of the fundamental is 6 meters long. In the pipe we have air vibrating, so we can find the speed of the wave in this pipe. V is just equal to frequency times the wavelength. It's going to be 56 hertz times a wavelength of 6 meters. That's going to give me a velocity of 336 meters per second. Give the first 3 possible harmonics on this pipe. Well, we know that lambda is equal to 2L over N. So if we just plug in different N's for this length of 3 meters, the first one is 6 meters. The second one is 3 meters. And the third one is going to be 2 meters. And to get the frequency, that's velocity divided by the wavelength. So we're going to take our velocity of 336 meters per second and divide it by each one of those wavelengths. That makes frequency 1, what we saw, 56 hertz. Frequency 2 is going to be 112 hertz. And frequency 3 comes out to be 168 hertz. And as we do that, that's twice frequency 1, and this is 3 times frequency 1. Next example, we have a 40 centimeter pipe closed at one end. So its fundamental frequency is 206 hertz. It's a closed pipe. The fundamental frequency is 4 times the length of the pipe. And when we're looking at it, we're dealing with a wave that has a node at one end and an antinode on the other end. That's a quarter of a wave shape. Quarter of lambda is fit into that length. So if we know that that's 40 centimeters, the fundamental wavelength is 160 centimeters or 1.6 meters. That's our fundamental wavelength. Calculate the speed of sound in the pipe. Speed is frequency times wavelength. The frequency we have here is 206 hertz. The wavelength is 1.6 meters. So when we do that, it comes out to be 329.6 meters per second. Give the first 3 possible harmonics for this shape. Now, the first 3 possible harmonics, when we are closed at one end and open at the other, N is going to be odd, so that's 1, 3, and 5. 1 looks like that. 3 looks like this. And 5 looks like this. Those are the first 3 things that are possible. And here we know that lambda is going to be 4L over N. So lambda 1 we already found to be 1.6 meters. Lambda 2 is going to be 4 times 40 divided by, lambda 3, because lambda 2 is not possible. It's going to be 4 times 40 divided by 4. So that's going to be a little smaller, 0.53 meters. And then lambda 5 is going to be 4 times 40 divided by 5, or 0.32 meters. We get the frequency the same way we did before. Frequency is going to be velocity divided by wavelength. First frequency was given to us, 206 hertz. The next frequency, frequency 3, is going to be 329 meters per second divided by 0.53 meters, 618 hertz. Frequency 5 is going to be 329 meters per second divided by 0.32 hertz, or about 1,030 hertz. If we look at that, the third harmonic has a frequency that's 3 times the first harmonic. The fifth harmonic has a frequency that's 5 times the first harmonic. Okay, so let's do it all at once. Closed pipe is 20 centimeters long. If that's the case, and we're talking about the third harmonic for a closed pipe looks like this. That is 3/4 of a wave inside of that length. So the wavelength is 4 times the length divided by 3. That wavelength comes out to be 4 times 20 centimeters divided by 3. And so the wavelength, when we do that, comes out to be 0.26 meters. So if I want the velocity for the air in the tube, I can do that now. Frequency times the wavelength, 1275 hertz times the wavelength of 0.26 meters. The velocity comes out to be about 340 meters per second. All right, last one, an open pipe. So it's open on both ends. Makes a fourth harmonic. So if it's the fourth harmonic, we're going to have 4 nodes. 1, 2, 3, 4. It's roughly going to look like this. If it's the fourth harmonic, we have 2 full waves. So if we have 2 full waves, that's 2 lambda on L. So lambda is equal to L over 2. So my wavelength, so L is equal to 2 lambda. What we need to do to find the length of the pipe is find the wavelength. The wavelength is the velocity divided by the frequency. So the wavelength here comes out to be 336 meters per second divided by 480 hertz. 336 divided by 480 is 0.7 meters for the wavelength. So then if 2 times 0.7, 2 times the wavelength is L, then L comes out to be 1.4 meters.